All right, let's see. Are we on at the scheduled time that we promised? I think we should be. Are we live? I gotta change my streaming photo. Coding and training a transformer from scratch in PyTorch. Okay, so we are live. All right, welcome to the stream. There's probably nobody here, but still welcome to the stream. Welcome to the video if you're watching on YouTube. Let's get this started. It's what the title said, what we promised to do, which is training a transformer from scratch. Well, implementing and training a transformer that is capable of tokenizing 3-digit numbers and summing them from scratch. So I just made the UV project with Torch, UV sync. That's it. That's the last we'll see of UV. It only has one dependency. So let's get started. Import Torch. I'd like to keep this single file. Probably not going to need more than this. Let's try to do it clean. So we know we need to add Let me just add a NumPy here. Sorry, I want to fiddle with this. Okay, so let's get it started straight up, right? So import Torch. We have a minimal file. It's the last time we have NumPy and PyTorch. Doubt we're gonna need NumPy. Maybe we will, maybe we won't. We'll probably just need core Python and PyTorch. So we need to implement a transformer in PyTorch from scratch without using pre-existing layers, but we want to use backpropagation because we don't want to do all the autograd. There's not going to be enough time. I'm going to have to do self-attention and linear layers, okay? So let's import Torch nn as nn. Because I need the backprop, I need to subclass everything from nn.Module, okay? This is pretty much the only trick we do here. So self, super, okay. And so we're gonna have to write an init and a forward for a bunch of these layers. Actually, there's only 2 layers that we need for the transformer. 2 core operations. We need a linear layer that's differentiable and has trainable weights. We also need the self-attention. And we're gonna have to register sub-modules, but that's fine for now. Let's start with the linear. So what do we need? We need a learnable weight matrix. This is all going to be a stream about tensor shapes, right? So for a linear layer, we need weights and the bias. And I think it's nn parameter. Yeah, so we need to use nn parameter. And Okay, so we're gonna need some documentation here because I don't know what these are, but parameters are class torch tensor subclasses. So how does their initialization look like? We're gonna have to initialize these. So to do initialize weights, but that's it then. So let's annotate the shapes then, right? So shape, because we're gonna deal with tokenized sequences, the shape will always be batch, length, and n. And the weights are gonna have a shape of n times m. Okay, for this layer. So then in it we'll take input dim, which is an integer, and output dim, which is an integer. Okay, and the bias will be torch random size input dim output dim. I mean, sorry, the weights and the bias will be torch random size just output dim because we add the output to the bias. Okay, this is done. So the shape of x is BLN. Shape of out is, let's call this in. No, x and y. Okay, will be BL out dim. Okay, so this is in dim. And what this does is it does y is x, it's torch dot mat mul x right multiplied with the weights plus the bias. We're gonna have to get the shapes right, which are probably wrong here. Let's see. Maybe they're not. Let me see. UV run Python import torch. If I have a torch random 4 5 16 and I have a W torch random 16 14, then torch.matmul xw has a shape of exactly what I want. Perfect. And if I have a bias that's torch random 14, torch matmul plus b, also broadcasts. Right? Yep. Okay, we're done with the layer then, with the linear layer. So we're almost done with the neural network part because well, we need the activation actually. Hang on. So we need a nonlinearity. Okay. Hey, thanks for joining on YouTube. From where, what? So we need nonlinearity. So we're gonna use, oh, I'm from the US. Let's define our own ReLU and let's have a torch tensor input. And let's return a y. And we're just going to do a pointwise, right? So y will be x times x greater than 0 to torch.float 32. We're going to need data types for all these. So D type is torch float 32. And X is a torch tensor. Yeah, I think I'm gonna stay away from backprop for now. This is just gonna be the forward part, but there is a tokenization that we have to do very soon. So stick around and thanks for watching. We're also gonna need a softmax on the last dimension of a tensor. Okay, so this will return y. There's a stability trick here. Let's see if I remember it. So the naive softmax on an axis. Let's do it on the last axis, right? Always. So it's E. Yeah, so it's the softmax weights. Okay, so it'll be y equals torch.exp of x divided by torch sum torch exp x, and the sum is taken on the axis, on the last axis. This is it. There's a trick though, because you want to do x stable will be, you want to set the min to 0 on each axis. So it is x minus torch min x on dim minus 1. And this is what we're going to use for stable softmax, if I remember this correctly. I guess we can broadcast this back. Yeah, so you subtract the same scalar from the last axis of x. Okay. So now we have, let me lint the code a bit so it looks cleaner. Sorry, UVX rough main. Oh, interesting. Oh, it's rough format. Okay, good. Very good question. Yes, the shapes, I always see them in order, right? So when I say first axis, it's the one on the left side, right? So if I have a shape BL in dim, now here's a trick. That's a very good question, actually. Thanks for asking that. So you count like in Python, 0, 1, 2, right? This is easy, right? 0 from left to right. So batch is 0, length is 1, dimension is 2. Except I try to never go above 1. So in my mind, this is 0, 1, and minus 1 from the back, okay? 2 is already too much. That's because you rarely deal with like 5D tensors, right? So if I had a 4D tensor, so let's say I had hidden dim, it kind of makes sense. So I will count this as 0, 1, minus 1, minus 2. right? And they kind of make sense because they're grouped like this, right? It doesn't really make sense to say that this comes, it's 0, 1, 2, because these are two different things. These are usually feature sizes. And yeah, so that's the other thing, because I like to keep, in my mind, feature sizes are at the end. So I count them negative, right? So that's why when I say we take, I could have written dim equals 2 here, because I know these are 3D tensors, right? But then in my mind, I actually want to say I'm going to take a softmax on the last feature axis, which also happens to be the last axis. So yeah, this is basically going to be a stream about shapes, right? Because we'll have to warp. We'll have to be very careful with the self-attention. I don't know if I remember how to do it without looking at the paper. But okay, we got the linear layer. This one's easy. We now have the softmax weights, which have exactly the same shape as the input. Except they all sum to 1 on the last axis, because I take something and I divide by the sum, so then it sums back on that axis. Yeah, that's pretty much the shapes. Okay, self-attention. Now, before we go into self-attention, let's remember what the application is, because it says in the description of the stream. We want to learn a neural network that sums two 3-digit numbers. We're gonna have to tokenize them, okay? Because, so what is the input length then for us? L. It's always gonna be 6 in the minimal representation, right? Because I have 3 digits followed by 3 digits. I don't need the plus symbol because I'm only going to train the network to do a single thing. Just sum 2 3-digit numbers. Now, if one of the numbers has just 1 digit or 2, like it's 1 or 27, I'm actually going to do padded digits followed by another 3 padded digits. So then, for example, the operation, what we would call 1 plus 3, the input to our transformer just becomes 001, 003. Yeah, thanks for stopping by. You can make sure you watch the recording later. If I have 27 plus 124, this is 027, 124. This is what my input transformer will see. And finally, for 3 actual digit numbers, I don't know, like 678 plus 321, the transformer will just see 678, 321. So then I know I pin the L to 6. What is the output length that we want? Well, before we get to that, so how many digits are there? There are 10 possible digits. So this means a vocabulary of size 10, okay? So what I'm gonna do is I'm just gonna create the vocabulary. Let's see, how should we keep this? Let's do a tokenizer. So then the tokenizer, what it does is it takes as input it takes as input A, which is a string, which represents the string representation of the first number with up to 3 digits. So A will be either 1, okay, so we can make this even more precise. So 1 comma 3, 1 plus 3, but 2 separate strings, right? This is how we're gonna tokenize. 27 plus 124, that means I have 2 input strings. The plus symbol doesn't matter because we only trained this, we hard coded for addition. Okay, so A and B are these strings. They could be up to 3 digits. And for each of their digits, I'm gonna pick the entry in a codebook, which is a torch tensor. And I'm gonna return a torch tensor, which should be output length of size L and input dimension or some feature dimension. Okay, so I just need the code book for this. That's fine. We can deal with that later. So return encoding. Okay. I forgot to annotate this with the torch tensor and a torch tensor. So now what do we need to do? We need to tokenize each individual. Oh, thanks for stopping by. Feel free to ask or lurk around. So we're gonna have to take these two strings, which are up to 3 digits, A and B, tokenize each individual digit. What tokenize means, so let's see, for and we're also gonna have to add padding zeros in front. Actually, let's do that before then. So pad with leading zeros. This is easier this way, right? So we're gonna say A is equal to 0 times 3 minus length of A plus A. So now 1 becomes 0, 0, 1 because I put 3 minus 1, 2 zeros in front of A. 27 becomes 0, 27. 6, 7, 8 becomes 6, 7, 8 because 3 minus 3 is 0. And the same for B. Good. So now I have 3 digits. Tokenize. Oh, that's a good question. Why do you prefer Torch over TensorFlow? I don't really, I think I got used to it. I don't think it matters that much anymore. I know TensorFlow 2.0 is, they basically copied PyTorch. It's probably out of habit. Although I will say one reason is I think it's a bit easier to switch between CPU and GPU. Like if you don't have the code you write is a bit more portable. Maybe I'm wrong though. And I think it has better multi-GPU support. Okay, so then we're gonna need, let's start another auxiliary, tokenize integer. And this one just takes a X, which is a string. Now we know this is, and no matter, okay, it also takes a code book, I guess. Well, no. And it returns a list of integers signifying which token entries, which entries for the codebook I need to pick. For a 3-digit integer, this is trivial because it's just list it's just integer of char for char in X. Okay, so now what's happening here is that something like 6, 7, 8 becomes 6, 7, 8. And then I can say A IDX is just tokenized integer of A, and B IDX is tokenized integer of B. And now once I have the indexes, I just need to index my code book. Okay, so A encoded, encode each number, tokenize each number. I could have done the padding after the tokenization, I guess. But the 0 makes semantic sense here because it's actually the operation 0. So it's fine this way. And then we'll have to do a torch concatenation here. So I got A encoded and B encoded. And this is what? My codebook has a size of... So I need to slice it on the first dimension. And everywhere else. Okay, and then interesting. So then the concatenation happens A encoded, B encoded on dimension 0. Okay, so finally now I have a sequence, a single sample of length and input dimension. I still need a batch operation though on top of this. Where do I put a batch operation here? This is where it gets hairy, maybe. Okay, we also need a code book. So define get code book, and it must have a feature dim, and also has a num entries. Now what I'm gonna do is, because I don't know how to get, we're not gonna make this learnable, so we'll just return torch randan of num entries feature dim d type torch float 32. That's it. So I just encoded my digits with random Gaussian vectors. Does this work like I think it does? 4, 4. It does. Okay, good. Okay, so we can actually start working on our main a bit now, because we can say get a code book only once. Now for us, the code book will be get code book. How many entries does it have? At least 10, because there's 10 unique digits. There's probably 11 because we need a mask token. But no, we'll do a decode only architecture. So we take 10 digits and predict 4 other ones, because summing 2 3-digit numbers can spill over the 4th digit. So the codebook just has 10 entries. There's no start or stop tokens, no conversations, no special tokens, right? No special entries, just the digits 0, 1, 2, all the way up to 9. There's no plus symbol, no equal symbol. We only need those if there's a minus symbol, because you need to discriminate between operations. Feature dim is, we'll put the 128. Okay, we don't know what to put this, so we can say feature dim is 128, and we can give it feature dim. I guess I might as well call this num entries. Okay. Once and for all. Okay. And we can make this. Yeah, this is fine. Okay. What next then? What next? We can encode, we can get a batch, we can encode a batch. Okay, so tokenize pair, let's call it, okay? And let's do the higher dimensional version of this, tokenize batch, which is I take a list of first operators. This is not the most efficient representation. We're going to run into computational trouble here probably, but we'll optimize that later. And this one is easy. Batch size will be length of A. Actually, I don't even need this, right? So now it's the user's responsibility for pair and zip AB. So for AB in zip, let's call these Okay, I'm just gonna make this directly batch then. There's no need to do two functions. We don't want to stay too fragmented, right? So we're directly gonna say for first, second in zip. Well, no, let me do it this way. For A, B in zip first. Okay, so we can call this first, and we can call this second. So now we reach into, we encode each number. I gotta store the tensor. Let me pre-create the tensor, right? So the output, I know I can pre-allocate. So it's torch empty. There's a special empty which errors if you don't allocate everything, I think. So this will be a good signal that we did it everything right. And it has a size of the length of first, which is the batch. The second side is hard-coded. We know it's guaranteed 6, not 3, my bad. So 3 times 2, which is shorthand for 6. Or 6 is shorthand for that. And the final dimension is codebook. It's the dimension, the last axis of the codebook, right? This is where it's useful to think in reverse again, because I know it's the feature instead of typing codebook shape 1. Okay, and then I can also get an I and the pair, and I actually enumerate the zip. Okay. And I just need to store this now. And I just return the output. Whoops. So I say output at the ith position becomes the concatenation, and I return the output. Okay. Are these D types? Where? Oh yeah, the codebook is the D type. Okay, good. So the D type flows from the codebook. Perfect. So this has the same D type. Okay, so now I can get the batch of numbers. But this is actually the input to the model. Let me make this even more modular. Okay, let's do it like this. So we're just going to tokenize a batch of 3-digit of numbers with a known number of max digits using a codebook. Okay, so the output will be the length of numbers. It'll be max digits, because I want to use the same function both for the input and the output, but the output may have 4 digits. When I sum 2 3-digit numbers, I may spill on the 4th one. So I'm actually going to need a more flexible function because I don't want to write another one. Okay, and then I just need for a in enumerate numbers, which is not a string, it's a list of strings. I'm just going to pad and tokenize and encode just that one number, and then the output becomes A encoded. A bit cleaner now. It's not 3 here though, it's max digits because I put the zeros in front, then I tokenize it. And I get the code book. Okay, good. So then this turns stuff like 6, 7, 8 into matrix of size 3 codebook dot shape -1. It's not 3, it's max digits because it may have padding, all right, including padding. Okay. Okay, this is much more usable now. I have my ReLU, I have my softmax. I just need one more component of the inner architecture, which is the beast, the self-attention. Problem is I don't know if I remember how to do self-attention. So I know it's a key query value thing. Okay, so I know I have 3 layers inside, 4 layers. I have key, I have weights for key, key, query, value, and output. If I remember correctly, I take the key and the query, which are the same, and I do a matrix, key qt, and I do a softmax, and I multiply with the value, and I pass it through output layer. Or actually I should say O equals this. Okay, this looks pretty good. I think I'm starting to remember now. So let me see a bit. These are all oh my god. QKV actually I think is the more query key value. I think these are all the same signal, right? So they're actually the same tensor, which is X, because it's self-attention. And they have a dim of Q will be batch, length, and input dimension. I know I want the dim of the output to be batch, length, output dimension. Because the self-attention layer doesn't change the length or the batch shapes. Okay. I know I want the... Here's the trickery part though. The dim of Q... I think it's QKT. I remember now. So this is, it's still a batch, it's LL. Okay. And then what it does is it for each sample in the batch, we do matmul between LL and the value, which is the same as the signal, L input dim, which gives us L input dim. And finally we apply the output layer, which takes us from L input dim. Well, I can write the batch here to batch L output dim. Okay, this doesn't look too bad. Now, how the heck do I store these layers in PyTorch? Because I have a linear, so I can just do 4 layers. Can I not? I can. Self Q layer is linear. So now what dimensions do I put for it? And how do I change the shape? Because at some point, so this self-attention thing, it takes L and also outputs L. At some point, I'm gonna have to take, so I start with 6 digits, but I need to predict 4. What operation do I use to change the L at some point? Is it just a linear layer on that axis? Could it be that easy? Okay, so we apply softmax on dim -1. This one's easy. Or maybe is it -2 or is it dim 1? No, it's -1. Okay, but how do I change the L shape? Is it that I start my value with what? The missing tokens? I think I'm gonna have to make something up here and I'll probably get it wrong, but in any case, let's... Okay, so the Q layer is... So what inputs do I need for this? I just need in features, input dim, and output dim. There may also be a hidden dim. Yes, there is a hidden dim because I want the layers to be of shape. So what did I do? X right multiplied. So the output shape. So this definitely is input dim, hidden dim. Same for all these other guys. QKV. No, hidden dim. Let me see. So you don't predict tokens here. Dim would be... Yeah, input dim, hidden dim. Yes, but how do I... Well, no, the batch is separate, but if I go in with 6 digits, because I want to do 2... At some point, I have to switch to 3, right? Because I want to predict 4 probabilities, right? For each of the output digits. So I know what the last dimension is. The batch is always in front. I don't know how do I swap the 6 from 4, because I go in with, let's say I go in with 1 2 3 1 2 3. I know the result of this should be 0 2 4 6. Because 123 plus 100 blah blah. So where do I go from? So this means I need to flip to input 6 tokens and output probabilities for 4. So that means my final output will be a matrix of size 4 and 10, because my dictionary size is 10. My input will be 6 and let's say 128. The 128, I know how to switch to 10, because that's the final layer, right? That maybe I lift this to whatever. How do I switch the 6 to a 4 though? And again, you can put a batch here. Let's say it's BB, but it's separate. How do I switch the 6 to a 4? Is it that my value is always 4? No, but that won't match the sizes. No, because that's not self-attention anymore. Because at some point I'll get to hidden, so near final, it'll still be B6 1024. So this I can drop down to B6 10. That's easy, but how do I drop the 6 down to a 4? Or maybe it's... The thing is, it's not necessarily down, because it's... Oh, wait a second. So in decoders, because they do next token prediction. I know what they do, because in LLMs, they always have a 1 here. Oh, so they just glue all of these together. Okay, so what they do in LLMs is they crunch this down to a B. Okay, I know how to do it, right? Because they do... Yeah, but I need a matrix output. So in LLMs, you have a single vector of like 10 probabilities. So what they do is they crunch this down to a 6 times 1024, and then they go to a B10. Now, what we need to do is we need to go to a B4 times 10 and split it back into B410 and softmax. Okay? So they basically, I need to collapse the dimensions very close to the output, then reshape them to my final size with a layer, and then actually shape them in a matrix, because I want to predict all 4 digits at once. I just want to predict the result of the sum. All right, it's not single token prediction. Okay, and then I get final output. I think this makes sense, right? Because in LLMs, they just merge. I'm pretty sure they merge these two together in pure decoders, because they only predict 1 token at one time. So they just need a 110 here. That's not true for us though. We're gonna predict 4 tokens simultaneously, right? Because I just want to do the calculation. So 6, 7, 8 plus 3 to 1. This should give me, I don't know how to do the math, but it's like 999. So, well, with a 0 in front. So I'll have to predict 099. And then I do cross-entropy simultaneously on 4 of these, which, speaking of which, oh God, I need to do the cross-entropy loss too from scratch. Okay. So yeah, let's keep the dimensions all the same. We'll keep a hidden dim, okay? But then the output layer flips it back to output dim, right? So the self O layer is hidden dim and output dim. Okay, and then I think the self attention is not too complicated. So in code, if I remember, QKV. So we have a Q, which is self Q layer of X, and whoops. Sorry, okay. And same for these other ones, QKV. I need to form. Yeah, so final layer has the, we gotta be a bit careful because again, we're predicting multiple tokens, but it's fine. We'll just predict a massive flat vector and then we'll split it back ourselves. So I need to form QK transposed. Remember, these have a batch too. So we gotta be a bit careful here. So these are all batch length hidden, right? Dim. So form attention coefficients, whatever they call them, or self-attention coefficients, self-attention matrix. I guess we'll just do coefs is torch matmul q k dot. Well, I need to transpose this. Torch transpose K -1 with -2. Okay, so I swapped the last 2 axes. Now I have a matrix of size BLL, soft coefs. Well, I actually have the softmax already because that's why I did it. So let's see, does this work here? So I take the X, I make a stable X. We need to do the stable softmax trick, otherwise it's gonna blow up. I think I got this right. I need to practice this. So, oh sorry, UV run Python. So let's say I formed the matrix, okay? So I have coefs is torch randn 644. Let's say it's like, or let's say, yeah, 644. Let's call it X actually. So then what is torch min? Uh-oh. Oh, torch min is so stupid. Oh my God. Torch min is so dumb. It has 2 outputs. Sorry, let's see. X min and nothing is torch min. I remember this. Torch min is so dumb. It returns the min and the arg min. I don't need. Okay, so now x min dot shape 64, which is fine. Yes, for last I need to stabilize only each. Right, so for, I think this is right? So, and then we do x table minus x min. Okay. And I do y stable. I want to verify that y stable is exactly the same as y. Oh, torch exp. What shape is x stable? Oh, I can't do this division here. Yeah, it doesn't know what to broadcast because it's, I have to do this then. Damn it. Okay, so y stable dot shape, and now y stable dot sum on the last axis should be all ones. Okay. Yeah, and now I can multiply this. I'm gonna have to do an expansion to multiply. Anyways, my point, let me check the y manually too. So plain y would just be torch expx divided by torch sum, torch expx, dimension -1, none. Okay, in this case, they are the same. This is good, but okay, good. So yes, we did stable softmax. What's gonna happen is if x has very, very negative values, like x is x times 1,000, I'm pretty sure the softmax is gonna crash. Yeah, there we go. So it gives you nan. Whereas now, let's try the stability then, now that we have it here. I really hope this works. Y stable should be stable. It is not stable. Am I forgetting the softmax trick? So what is x stable? I think it's the other way around. It's x minus x max. I think you want to set the max to 0. So all the numbers are negative. Oh, yeah, because you have explosion otherwise. Okay, fine. So torch.max x dim -1. Same thing. Let's see, does this work? X stable. What does x stable look like? It's gonna look shrunk now. Yes, because e to the minus something negative. I see, and it shall be very good. Okay, so now this is stable because just one number dominates from there because the differences are okay. Perfect. So we have stable softmax. Otherwise, we would have spent like hours debugging this because I thank God I remembered it. So I can just do softmax then on that axis. Okay, I have the soft coefficients. Okay, now these are also shaped BLL. Now I just need to do the inner matrix multiply, right? So I need to do, so BL hidden dim for the values, right? So modulate values. So then I'll say Y. Well, actually I can call it output already, right? Torch, I don't know if a matmul works here. So how do we multiply? Oh, no, I think it does. Yes. Okay, it does. Never mind. So it's just soft coefs and V because it does it on the batch axis, right? So this is a BLL times a BL hidden dim gives you a BL hidden dim. Was I supposed to use activations here? After each layer, maybe? I'm not sure. I'll use it here so I can put ReLU output. And finally, I have to pass through the output layer. So output is self.o layer of output. I think we're done. Pretty much, hopefully. Okay, so let's do the class transformer, which is the higher level. So this has to piece everything together, right? So it'll take the digits, tokenize them, pass them through. Okay, so what do we need here? So we need a, I guess we can call it num attention blocks. Okay, so I guess layers. Let's call it blocks. I like to call it an attention block. There's another trick here. It's output plus. I need. I think I need a residual skip here. Yeah, I'll do a plus v here. Or is it ReLU of output plus v? Nah, let's keep it like this, okay? So I'll do a skip over the v here, just to add more representation. There's probably other skips I'm missing. Maybe not, actually. No, this makes sense. Just the v, right? Yeah, you can't rely on these other ones. Okay. So I need number of attention blocks. I think that's it, because everything else... Well, okay, sure. I'll have a hidden dim for the entire transformer, which passes it down to each layer. I guess I need an output dim too, the final one, which is the discussion we had earlier. Super init. We'll figure out what to do there, and define forward. I guess we'll do the encoding on the outside, right? So forward x, return logits, let's call them. All right. Okay, we're gonna need a loss too. We'll have to write the logits. Okay. So what do we need in the transformer? Well, we definitely need... So how do I register modules in PyTorch? Because I'm pretty sure this doesn't work just writing it like this. Is it self.register? Yes, module. Oh, which is a function for add module. Add a child module. The module can be accessed as using a given name. There's a problem, I think, in PyTorch with... Let me do so self... No, I know the register one. Oh, I see. So it's Q layer. Okay, there is a trickery here. So it wants it like this. And now I can rely on Q layer. Otherwise, it doesn't see it right. I'm pretty sure otherwise gradients are not going to flow properly, and it's going to take us a long time to debug that one too. If I remember PyTorch correctly. You need to manually register them. And this one too. But this one is this. Okay, this is all good. Now, what the heck do I need to register here? Because I need to register... How do I register a list of modules? I guess there's a module list. So nn.Module... Oh, yes, there is a module list. So modules it contains are properly registered. Okay, so we gotta be careful here too. So we can say like this, self.attention blocks is nn.Module list, and it is a list of modules. Each of them is a self-attention. I guess they're all hidden dim, hidden dim, hidden dim. We're not going to complicate. And we need how many of these? Number attention blocks. Okay, so we got all of them. We need a first one that raises input to hidden dim. Yes, we need that one too. Okay, so then self in layer will be a linear input from input dim to hidden dim. I guess I called it in dim. Okay. Okay, fine. I guess I'll call it in, and out. Okay, except I need to do the, damn it, register module. And finally, we have also an output layer. Which takes it from hidden to output. We have to remember this output is special because it will be it's actually 4 times the number of we need to pass 40 here. So we need something else here. We need a self dot output sequence length. Oh god, this is horrible. Output length or logit. Okay, because we're gonna have to reshape the output to actually be a matrix, and we're gonna have to logit length. I don't like this name at all, but sure. UVX rough format. Okay, so we cleaned up a bit. Now, what are the operations? Because we have all the layers. I'm just gonna take X and I do self.in layer. And we have to trust that this works. Yes, because it's a registered module. Yeah, so that's it. This is what I need. Okay, so this is good. X. Okay, so now I raised my X. Which is a sequence, but it doesn't matter because my linear layers, they work on any dimensions. Yeah, they do. They just modulate the output dim. Okay, and then for, I just do the attention blocks. So for block in self attention blocks, X is block X. And X is self dot output layer X. Logits will be X dot reshape. So actually I need it differently. I don't need output dim then. I need it specified its code book length. And then I want this to be the product of code book length times logit length. Okay? And I'm gonna store these two here. Self code book. I guess it's dictionary size is a more common term these days. Okay, so then all I have to do here is I need to reshape X to the batch remains. I just have to reshape this to logit codebook length self. And now I predict 4 tokens at once, finally. I have logits for 4 tokens over a codebook space of whatever this is. right? For sure. Okay, good. Let me format again. So now I can finally do the transformer all the way here. Oh, I need the loss function though. Oh yeah, I'm gonna get bit by the loss function because I don't remember the loss function. So let's do it here then, the loss, because it kind of comes last, I guess. Define cross-entropy loss. Okay, so it takes as input logits, which is a torch tensor, and it takes as input labels, which is also a torch tensor, but it's a tensor of integers. And it returns a torch tensor, which is a scalar. Well, no, a batch. Okay, so what does this do then? So let's see, return loss, okay? Hey, thanks for stopping by. Thanks for saying hi in the chat. This is going pretty fast, a bit faster than I thought, but it's probably not gonna work. So we'll have a bunch of debugging to do. Maybe we won't. And we still have to create the data set, which is easier than it sounds because it's we're adding 2 3-digit numbers. So we just have to randomize some data. I need the cross-entropy loss though, and this I don't remember at all. So I know my logits has a shape of batch, length, and codebook, okay? Or let's say num classes, because this is the classical notation. Now, my labels will be batch, just batch. No, let's say it's one hot labels, okay? So one hot encoded. So, well, if you're interested in learning ML, this is literally one of the more basic things, because one hot encoded means just a single one in each row, because we have B rows, num classes columns. Okay. What the heck do I do with this now? What is the cross-entropy loss? I believe it's just minus logits at label. Right? Because I want to minimize this. So I want to maximize that logit at that label. And nothing else matters. Okay, so then it's not that hard then, I think. It's just logits. I guess it's sum logits times labels with a none on which dimension? -1. And this just gives me the last logit, so this gives me BL. But now I'm doing simultaneous prediction of 4 digits, and I want to simultaneously maximize all of them. So I'm just going to do again sum of result again on the last axis. So this gives me just the loss for each pair of numbers that I want to sum. Okay, I think this is it. So we just need to make sure we encode our labels with the one hot encoding for each digit, which is, again, probably sounds easier than it is. Yeah, you should not. I try not to use too much Gen AI. I don't really do it on stream either. I'm not sure what to tell you there. let me see here. So I think this is way easier than it sounds, right? So I just take the loss is logits, it's torch.sum. I mean, there's probably an even simpler indexing way I can do here, but I'll just do it algebraically because it's... -1, -2. That's it. It's just that we need to encode the labels. Okay. So for this, we need to encode... We need another function that so we need a one hot encode integer, okay, which takes as input x, which is a string, and it outputs a torch tensor, which is a matrix of ones and zeros. So for example, for it also needs a max digits. So for example, because we know we need to encode 4 digits because the sum of 2, 3, it can spill over. So 6, 7, 8, we actually want to encode 0, 6, 7, 8. This is going to be a matrix that on the first row, it has a 1 and 0, blah, blah, zeros. The second row has 0, except for a 1 in position 6, then followed by zeros, and so on and so forth, okay? So what we can say is, and codebook size, I guess. Codebook dim. So we can just return output. I know for sure the output will be... Do I have a padding function here? Oh yeah, I'm gonna have to pad again here with leading zeros. So we're gonna pad the number with leading zeros. Okay, let's call this A. And then the output, we know we can pre-make it here. So it'll be torch zeros. It'll be d-type torch int, or I guess long this time. And I'm gonna have to convert it to float. Well, let's do it this way then. Let's just keep everything in floats, right? And I know the shape will be max digits codebook dim. And all I have to do is one hot encode each digit of A. So 4 digits in A. I'll tell it to do output, I guess I. So we're gonna take all the characters, and the ith row and the digit column will be 1, 0. I think this works in PyTorch. You can assign 1, 0. Let's see. UV run Python import torch. Output is torch zeros 3, 4. D type is torch float 32. Output. And I can say output 0, 2 equals 1, 0. Yes, I can. Okay. Good. So it's from 0 to 9 are the digits, and then this has max digits. Oh, sorry, it has codebook dim, which is 10, and max digit, which is the number of digits in A, which is automatically padded now with zeros. And this encodes a single integer. I don't know if we can do this in a batch though. Batch is always gonna be a problem. Is it not? Yeah, it will be. So I guess I can do this. I don't really need I just need a list of strings. Not too happy with this. Numbers, and we can say, so I know I can form the output first, but now it also has a length of numbers, batch, and I can say for I guess I'll call this enumerate numbers. I gotta switch the index, so careful there. Path with leading zeros for j, and its output I j. Yeah, this should be still reasonably fast, right? It's not the end of the world. I think this is it then. Yes, no, maybe. Interesting. Okay, all right, so I got cross-entropy loss. Okay, yes, now we need to generate some data. Let's keep writing here. So, generate data. So how many samples do I want? Just an integer. And that's it, okay? So we're gonna make this return a tuple of integers. 3 of them specifically, right? The first operand, the second one, and the result. So we'll have to store like first, second, result. No, it'll be, sorry, it's a list of tuples of integers, right? It's a list of triplets, right? Because we want to mass generate data, okay? So return samples. I'm just gonna do this the dumb way then. So samples will be empty, and for sample in num. No, let's not do it the dumb way, come on. So let's see. First is torch rand int. So what do we do? From 0 to high 1000 because it's one above. And how many? Size? Num samples. Okay. Second, torch rand int. Exactly same thing. So we're summing numbers. And result is first plus second. Now we have to convert these to strings, right? Okay. So we have to do, oh shit, I need to convert numbers back to strings now. Results, yes, result. So now I have samples number, blah, 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 samples. Algebraically sample date, sample algebraic data, sample data, sample underlying data, let's call it this way. I have to convert to strings though. Which is not the best, right? I guess let's work. Yeah, I have to convert. Okay, is there a cheap PyTorch way that I can convert to strings? UV run Python. So if I do import torch and I have num samples is 32 and I have 32 integers now. Oh, I can't do first numpy string, no. String of this, please. Nah, but it's a string of the whole array. So I have to do it manually then. String of lm for lm in first. For lm in first dot numpy. Yeah. Okay, so then I can convert this to a list of strings. And then I have to pair them too. We'll just do it the dumb way then. Yeah, there's not enough time. I guess it's literally just this, right? Yeah, we have to do it for everything. Just don't know if there's an well, there is an efficient. Okay, maybe if we have time to optimize this, we don't need to go through strings at all. We should directly go from integers to indices. So what the heck do I need? Oh, look, I can skip this step. If I could get 6, 7, 8. Okay, so is it easier to split if I have a thing like this? Yes, it is. I can directly sample digits. All right, this is it. So I don't actually, okay, good. So instead of sampling numbers, I'm just gonna sample the digits directly of 3-digit numbers, right? So num samples and num digits, int. So then I say, I just want a matrix like this, which is still 3-digit numbers, but they're also, it's even better, they're pre-padded now. No, they're not pre-padded. Yes, they are pre-padded. Yes, because I can sample 00. Yes, I can sample 004, for example, by itself. I can also sample 444. Am I messing up the probabilities though? I don't think so. Nope, the probabilities are still uniform, right? Yep. The sampling uniform is the same as sampling digits. Yes, that sounds right. It must be true. Okay, this is like a basic question. Oh, no, but I need to form the result. Damn it. No, wait, so I tricked myself. So no matter what I do, I need to form the result. So then for the result, I need integers, unless I encode the addition manually. This is so annoying, but this is part of an efficient pipeline. It has to be done. What should we do here? So I sample digits. Okay, I can form the numbers. Okay, so fine. First numbers is torch zeros. And the size will be, sorry, we're gonna do some warping here. Okay, second numbers. I'd rather do PyTorch operations though than string operations. I think that's a good lesson to learn. Now the result will be first numbers, second numbers, except I have to populate this, right? So for digit in range num digits, first numbers are first numbers times 10 plus first at the digit. Okay, so I start from zeros and I put the first digit to the left, like a 1. Next time I multiply, it becomes tens. Okay, so I just push the digits, right? So becomes 0, 0, 1. Then next time it becomes 0, 10 plus 2, which is 12. And then the last time it becomes 1, 2, 3, which is exactly what my digits were. Okay, good. Yeah, I would much rather do this than result values, right? First values. I'd much rather do this than manipulate strings. Now I also need the reverse method. And actually there's an optimization here. These loops can be done together. I can push digits simultaneously because they don't interfere with each other. Okay, so I got the values. I need to write back the result. There is a problem though, because the result may have 4 digits now. So I know the result will be torch zeros. It's going to be size num samples, num digits plus 1, because when I add 2 numbers of size num digits, I can spill over, okay? And I say like this. I mean, this is just basic, right? So for digit in range num digits plus 1 now. I have to put these from the back. Result dot 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 at minus digit. Wow, this is so annoying. Hang on. Plus 1, because 0 becomes minus 1, 1 becomes minus 2, num digits becomes minus num digits plus 1. Yes, that's correct, because it has 1 more digit. So the last digit of this is the modulo. Please say there's a torch mod. Remainder. So torch remainder of 23 divided by 4. Oh. So let me see the documentation for remainder. I don't know these by heart. Oh, input other. Okay, so it's remainder Python's modulus. So A, B has to be a tensor too. So it's the remainder of result and 10, which is a torch tensor 10. This is very annoying. This is a D-type torch long. I need to take care of data types a bit here. Okay, now sorry, we're getting in the engineering part a bit, which is more annoying. Okay, and I have to... Whoops, sorry, result values, right? And result values has to be... Is there a torch floor? There must be, right? Result values divided by 10. Okay, this is getting kind of sketchy. So let's play a bit with it. So result values, let's just sample some values, right? Because we know the sum of 2 integers will be between the 2 3 digits, between 1 and 1999, between 0 and 1999, 1998 inclusive. Okay, so we sample 8 of these. Okay, result values. So now we say, okay, so I can just do this then. Num samples is 8, num digits is 3. Result, I can just copy this then. Oh no, because I don't know how to do a so let me see what happens. So result values, torch remainder, result values, torch tensor 10. Does this work like I think it does? Yeah, it does. It gets the last digit. Okay, so it's not bad. So then I put the last digit at the end, and then result values becomes torch floor. Result values divided by, why did I write the 10.0 here? Because it's a 10. And this now, oh, seriously, floor has, it returns floats. Returns a new tensor, the largest integer. Dude, how come it returns floats though? Like, this is insane. Who coded this? Because it says the largest integer. I hate it. Oh yeah, even the docs, it's not an, this is not an integer. This is a float. I have to force cast it then. Torch.long. Annoying. This is very inefficient. Okay. So then we store the results, boom, 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 up to 4 digits, where this will become 0 eventually. 1, 1, 3, 4, 2. Yeah, we ate the digit here, right? Good. 5, 6, good. And that's it. So now here's the trickery. I can just return the indices, right? Because it's a list of tuple of tensors. Well, it's a tuple between a tuple and another tensor. So my convention will be, I'm going to return... No. What am I doing here? Sorry, it's a tensor. It's a tuple of tensors. Sorry. Because I'll tell you what I'm doing here. I can concatenate these right now. So I can just return... I'm going to return the result values, but I can do torch.cat first values, second values, on which dimension? -1. Right? Because now I have 6 digits there, and 4 digits here. Okay, this is very good. So now I can say generate data. We can actually look at this now. Okay, so inputs, so operands and result will be generate data. How many samples? I guess we'll train on how many pairs of numbers? 10,000. Okay. Now we can actually run our program. So we can simplify. This is pretty good because we got rid of strings entirely. We're not gonna need to. What? Oh my God, the digits, of course, right? Because I need to tell it. So 3-digit addition. Oh, actually, now the script works for any digit addition. Okay, good. So we have operands, which is what shape? No. Why? Why is it not? Oh, sorry, it's first, second, and result, because I want the digits directly. I don't want the numerical values. Again. Okay, and result.shape. So for example, if we look at one data sample, let's say the 345th data sample. This is 914 plus 855. And if I look at the result, it should be 1,769. That's exactly right. Okay, except they're all longs now, which means a lot of things. I'm not working with strings ever now. So actually, hang on, we can cut a lot of this crap now. So this function is completely unnecessary. I directly get the list 6, 7, 8 now. I don't even have pairs, right? So now my numbers is just a raw tensor. I don't even need... I don't need to do padding anymore at all in string space. I don't need to tokenize anything. I just need to encode. So this is directly encode batch. The secret that I did is I directly generated tokens, right? So I need to encode the batch. I don't need to know what the max. Do I need to know what the max digits are? What do I do with this output? So now I just do. Well, I don't even need a for loop. Oh my God, hang on. This is getting way too simple now. So whoa, wait, what's happening here? Oh, actually we're stuck here. So I have operands and I have a code book. What is the shape of the code book? Okay, so then what I need to do is I just do code book of operands. Yes, this works. So this gives me the encodings of 10,000. Yep, 10,000 pairs of samples. That's 6 digits, right? So that's it then. Actually, this is okay. So there's no, okay. I did the optimized version without even realizing, right? So encode batch just becomes return. It's not even worth a function anymore. Code book of numbers. We'll just leave it for now. And then I can just enter with my transformer. Okay, so now what do I need to do? Hang on, I need to train this model, so I need an optimizer. Well, so first we need to split data. By the way, there's a thing called training and sampling data, right? So train IDX will be torch rand int. I need a fraction. Train fraction, let's put it 0.8, okay? Well, let's just do train size then. Train samples. Will just be integer. We're gonna round 0.8 times the total num samples. Hey, thanks for joining. Thanks for stopping by. Okay, so then we want this many train samples. Now, again, we're not allowed to use NumPy or anything, so we're just gonna have to manually sample everything, but this is part of, it's fine. So I'm just gonna sample from num samples. That's it. Size. Actually, hang on. I need the torch choice or something. Please say it has it. Well, this is not good. Does it have a Bernoulli, a coin? Can I toss a coin for each? No, I just want to... Can I not do like torch random dot choice? I think I'm gonna have to peek at the documentation because I have no idea how to do this in basic choice. Like, I need to sample with exclusion. That's the problem, right? Because if I just say train samples, I'm just gonna get duplicates. And does this thing have... It doesn't have... Return tensor from random image to the shape of the tensors. Torch, keyword arguments generators. Damn, I really don't want to look online because I've made it so far without looking online. Come on. How do I do it? Torch. I am allowed to look at torch docs through Python though, just because I want to. Let me see what random has. Is there a choice? No. Is it called Bernoulli? I see it. It's a permutation. Okay. I kind of peeked at it, but sure. Okay, so what we're going to do is we're going to permute the numbers, and then we're going to pick the first train sample ones as... we're going to permute... Oh, there is a Bernoulli too. I don't know the syntax, though. Let me just permute everything. How about this? So I know I have... Okay, so we'll do it this way. So if I do shuffled equals torch... Actually, I think there's a shuffle too. Torch rand perm. What arguments does this take? N. Oh, okay. This is what I want then. It's just N. So it's just 100. Okay. Yep, and it gives them to me in order. So then I know that, okay, so I need shuffled IDX is just the permutation of samples. And then my train IDX is just shuffled IDX all the way up to train samples. And my tests, my validation IDX is everything else. Thanks for stopping by the way. See you two there. I'm so dumb. It's train samples. Okay. Okay, so now we have data. No, we don't have data because I need train operands. Train result is operands at the train index and result at the train index, and same for validation. Okay, we need an optimizer, and I'm not implementing Atom or gradient descent. So, because again, I'm not doing backprop in this. I just the forward and the tokenization from scratch. So for that, I need from torch.optim import Atom. We're just magically picking Atom. But before that, we can't do an optimizer without the model. Okay, so get model. This is the big one. So model is transformer. Now, how many number of attention blocks? I don't know. We'll just put number of attention blocks. 4. What else do we need for it? Yeah, fine. I'll do Atom W because it's better. Fine, I'll accept that one. Atom W should be strictly better than Atom. Ada, Delta, or whatever, it's pretty... Nah, those are pretty old. So we need a model. And what else does the model need? Now, input dimension, I know what it is. It's the code book size. So it is called feature dim. Hidden dim I get to pick myself. And I'm gonna lift the code book up to 256. You know, just go from 128 to 256. Let's make it 1024. Let's make it larger. What else do I need? Oh, I see. I need a number of digits here. Very important, because this will play a role in the output now. Because we need the output shape of the transformer, like we had talked earlier, to be exactly... what do I have here? So codebook length is a hard-coded 10, because I know I want 10. I have 10 digits in the world. Okay, 0, 1, 2, all the way up to 9. There's nothing else I can do there. I'm not even gonna bother hard. I guess no, it's not. It's num entries. Sorry. Okay. And then the last one is logit length, because I want to predict 4 digits simultaneously. So this one will be num digits plus 1, because again, like we've said many times, if I sum 2 3-digit numbers, the result may spill over on the 4th digit. So I need to predict all the 4 things. Now we do the big one, model.CUDA. Okay, we put it on GPU and we put it in train mode, although it doesn't matter. Which reminds me, I need to use dropout, which I did not do. There's no time. I'm not going to do dropout by hand, although that's kind of the point, but later. I don't even know why I need this one hot encode integers. I do not, because my integers are already... Oh no, I need to one hot encode tensors now. Okay, so now remember, because we converted, now we're gonna enter with 6, 7, 8. Okay, and I want 6, 7, 8 to become something like, depends on the max digits. No, because I know what I'm gonna enter padded if I enter. So then we want, well, hang on, because we need batches and everything. Hang on. We need the because I'm not allowed to use, I'm not gonna use data loaders either. I'm gonna do batching by hand. So this is just a torch tensor now, and it has as many numbers as the first dimension. I just need to convert the columns to be one hot. This is a tricky one, actually. How do I do this in pure PyTorch? So let's say I have this. Let's say I have, so let's say, because right now we're working with digits, right? We are gonna say we have, so rand int from 0 to 10. So let's say I have 4 numbers of 3 digits each. I need to encode these to one hot. So I want the result to be 4, 3, 10. And I want to inflate the result. There's a trick here. There's a very efficient trick here. So how do I get this to become 0, 0, 0, 1, 0, 0, blah, blah, blah. Like each of those has to be inflated. Come on. What about this one? If I create a BX, if I create a reference, which is torch, the range from 0 to 9, repeated with a trailing axis, repeated 4 times. Okay? So now it's just to do exactly this. If I now do AX inflated equals BX inflated, oh no, reference, almost, I got the inflation wrong. So AX inflated is reference, yep, this is the one hot encoded. Okay. Yeah, there is, but I'm not allowed to use it. I want to do it myself. I basically didn't use anything other than torch and memory in this for the remainder for this stream, except maybe I looked at some, probably when you came in, that's the only time I looked at the rand perm docs. And maybe some register module. So this is it. So then it's to torch.long. Yep, this is exactly what I want, because now I've inflated. Okay, so yeah, this is a trick. I compare the integers with all the possible values, okay? And I do some, let me see if I can explain this better then. I do some axis manipulation. So I'm leveraging torch broadcasting. The only reason why I want to go through this is because this is going to be efficient on GPU, right? Because we can do all these on GPU. So our function now becomes max digits. That's all I need then. No. I just need the codebook dim. I don't even need to know how many there are because I'm just going to compare everything, okay? So what happens is, so now this assumes my numbers is a torch tensor with a so let's create the reference. Torch range of the codebook dimension. Okay. And I'm going to make this have a fake 1 in front. Okay, so now the shape of this is one codebook dim. Okay, so it's 110. Then what I'm gonna do is I'm gonna repeat it what did I repeat it for? Reference. Oh, for each sample. Okay. So each sample. Okay. So then this becomes batch codebook dim. Okay. And now I do the comparison. So one hot encoded will be numbers. How did I do it? Because I always get these wrong. This is how I did it. With the fake one in the back is equal to the reference with another fake one. Hang on, we'll talk about this right now. And I convert this to... Actually, I needed float even because I'm going to do... Okay, that's it. So what this does is it compares what? So numbers is batch code... No, it's batch num digits, which is hidden. It puts a 1 in the back, okay? And it says, is it equal to something of the shape which we just created upstairs there? Batch 1 codebook dim. Because it puts a 1 in the second dimension, okay? So now when PyTorch sees an operation like this, the batch matches. And when you have mismatched... This is called this is the basics of broadcasting, right? So now what's going to happen, this is a way to encode a double for loop, except you do it all at once in parallel, right? Because they'll say, oh, for each digit, I need to compare it to the code book. Sorry, each value in the digit. So for each digit, I'm going to compare it with each value in the code book. And I'm only going to return true if they're equal, false if they're not. And then when I cast that to float, that's 0, 1. So this is exactly the one hot encoding. We're done. I don't think I even need encode batch. This is trivial. Okay, so let's proceed with the transformer then. So what do we need to push through the model? So we have train data, we have model, we have optimizer, Adam W. Params will be model.parameters. And I'm just going to leave the learning rate at default. I don't care. And that's it. Training loop. Training and validation loop. Okay. So we're going to say batch size, num epochs. Maybe this is the wrong way. Num epochs batch size. Looks cleaner. We're going to train for 10 and 32 batch size. So for in range num epochs, let's call it epoch index. Well, you know what? I like actually nobody. No. These days you think in terms of steps, right? So let's not even bother doing the nesting. So for step index, at each step, we're just going to sample a random batch from the data without replace. Again, I have to do the shuffling then. Damn it. Okay. We're just going to sample a random batch of data, possibly with duplication. I don't even care. Okay. So sample a batch of data. Batch. What is it called? We need to sample both the... So batch indexes will be torch rand int from 0 to the length of the train operands, and the size will be batch size. Okay, now we actually need to get the data, right? So batch operands and batch result will be train operands at these indexes and train result at these indexes. logits with model. So output logits. And we need one hot encode expected results. Okay, this is the only place where we need to. So one hot result will be one hot encode tensors, batch result, and the codebook dimension. How many digits are there? Num entries. Okay. And the output logits will be model. And it just takes as input the... Oh, no, sorry. So encode. So we need to encode the inputs using the codebook. So, or let's call it encode inputs to tensors, right? Now this is where we have the tiny function, which we can finally eliminate because it's so tiny. We can just do this line here, right? So return, okay? Return, right? So input, or let's call it batch tensor operands. Ugh, okay, fine. It is the codebook at the batch operands. And then the model predicts logits using the tensors, loss function, backpropagation, and model update. This one is the classic one. Loss, what is it? Model, zero, no. Optimizer, zero grad, loss dot backward optimizer step. Finally, we need to tie it all together with the loss. What do we call the loss? Cross-entropy loss between output logits and the one hot result. And validate. Okay, so now validate we want to do with torch no grad, classic. We have to do with torch no grad. I have to do the same thing. Sample a batch of... I wonder if I should functionalize this. Well, I guess, okay. So, sample a batch of validation data. But we don't need the one hot anymore. We can just peek at the result and try to... Oh, I see. So, for validation, we don't need the result. We just need val operands. Because we're just going to print the result. We're going to predict and we're going to take the max probabilities predicted by the logits. Okay. Encode inputs to tensors. Predict logits with model. Now here's where the flow gets different, right? Decode which digits, decode predicted codebook entries, which are called digits for us. So decoded entries is, I believe, torch argmax is just torch max output logits dimension -1 and form digits into numbers. We're gonna have to form the operands and the decoded entries, and then we're just gonna print in the form of, and it better be right, like it'll be something like first plus second equals result. Let's call it first value plus second value is result value. So I need a mini function that decodes these then, right? Because I have a batch. And we'll just do one then. We'll just sample one. I just need to form these now. So batch operands, I know there's 6 here. So I need to split them back into the first 3. Do I have a routine for that? I do have it. It's the 10 thing, right? Where is that? Here it is. No, it's not this one. It's the other one. This one. I need to functionalize this. So digits to values. So it takes digits, which is a tensor, and it also returns a tensor, but it has a crunched axis, right? So it says for digits in for I in digits shape. So this is the number of digits, and it says values will be torch zeros. Is it 0? No, it's zeros. Digits dot shape, because that's it. It takes, yes, and it does values is values times 10 plus digits. Slice this one. Return digits. Okay, so then I can do, probably not even worth doing this, but sure. Let's see, did I do this right? Size, I guess D type, torch.long. Yeah, why do I need num digits? Oh, I knew it because it's +1 there. Gotcha. Okay, so then I can just call its digits to values of first, and this is digits to values second, and I don't need all this logic anymore. The result values are sum. Whoops, I have a code error. Okay, so finally I can go back my validation data, because now I know, now these are 2 crunched operands, right? So first value will be digits to values, batch operands, everything but only to the 3rd digit. Second value is digits to values from the 3rd onwards to the 6th one. And if I got it right, and this is argmax, then result value will be digits to value of the decoded entries. And I'm just going to squeeze them. CPU.numpy so that they print nice. And I think this should be it. The print should be, this is it. Format. Oh, seriously? 152 where I have a syntax mistake? What? Sorry, what is happening here? Parentheses was... Am I blind? 152, 45th column. Oh, it's a comma here. Duh, I'm blind. Okay. Let's print the loss too, I guess. Oh yeah, I need to do loss sum dot backward. Very good catch here. Right, so I can print step index loss loss dot sum dot CPU dot well, I guess it's dot item. I don't remember what the syntax is with 4 floating point decimals. Something like this. Well, if I don't remember the syntax, I'm not allowed to look it up, so sucks for me. And I do UV run main, and it's probably not going to work. This is the first time we try to run this. Okay, so we're stuck at generate data now. Okay, so now we got to fix the bugs. I'm going to get this running. Oh yeah, I don't need the val result. Oh, I forgot to split my data properly. Okay, almost messed up here. We just need val operands, of course. Very good catch. So, generate data. What's happening here? I sample digits. Where's the error exactly? Result 168. Huh. Number of size must be greater to the result. Size. Digit. Minus 1. What the heck is happening here? It's always shapes, which is not the worst issue to have. Result.shape. Right, because I want to put the digits, the results have 4 digits. And the result values are 10,000 of them, right? Oh, this is the mistake then. Whoa, so what is first values? Oh, what? My function is not right. Oh, the return values. Basic mistake. Try again. I forgot to save the file. This happens. Oh, super init is always self, I think, right? If I remember correctly, probably. Obviously. And actually, I don't even know what the syntax is. Well, this is a problem because I don't know how to call. Okay, I have to peek at this because I don't know basic Python anymore. Sorry, how do you call? Is it super? Oh, it is. I'm so dumb. So it's super. Okay, so I had it right here and wrong in the other 2 places. Okay. My bad. It's basic syntax. You won't get docked for this. I forgot to initialize my transformer. So I'm not initializing it right. So where's the transformer? Okay, I'm getting so it takes 1 positional, but 2 were given. 1, 2, 3, 4, 5. Is self not in init? Yes, it is in init. Of course it is. 1, 2, 3, 4, 5. So I don't understand. I don't have to feed self to that? Oh, maybe I don't. Sorry. It's just a plain init call, right? Okay, still struggling with basic Python, maybe this time. Okay, very good. Ran then. Random doesn't have D-type? It does have D-type. Oh, but no, here. Ah, I know what I did. Sorry, I put it wrong there. So I close here. Okay. Like here. And here. Right, yes, because it's parameter with values. Almost. Very good. We forgot to put data on the GPU. The most classical error. So that means we're basically there yet. So where we put data on GPU? There. Batch operands, one hot result. Dot CUDA. Well, there's a more efficient thing here. Let's just put the codebook on CUDA. Right? To CUDA. So then codebook is on CUDA. Batch operands has to also be on CUDA. Which is maybe not... Yeah, we have to move this. This should flow now. One hot result also has to be on CUDA. So actually, let me move it here because it's nicer, right? What do I do with batch result? Oh, okay, so I can move this early then. Okay, so it's cleaner. Because this one, and num entries is what? So I make a reference. Torch a range device equals numbers.device. Okay, so it's time we crunch up the engineering a bit. Because we want to stay on nice devices. Again. Almost there. Yep, we're at the last layer. There we go. We made it all the way through the model. What the heck am I doing wrong here? Logits equals. So I messed up the logit reshape, right? Very good. Pretty easy to fix probably. There we go. So let's see what happens in the neural network, because the output layer has a size of... What is the output layer size? Out layer. Oh, it should have codebook length times logit length. Maybe this is better in reverse because they're ordered like this. So it goes from hidden dim to logit length, codebook length, and batch. Okay, let's see what the shape is. We're messing something up here, but it's... Yeah, 32, 4, 10. Oh, and why do I see 7680? Oh, that's the issue, right? Oh. Sorry, what? So self dot logit. So this line works? No, it doesn't work. Oh, so whoa, wait. So my shape is way exploded here. So my out layer doesn't work? I thought the out layer was... Oh my god. I need to flatten it. Ugh, of course. There we go. So x will be x dot reshape. Hey, thanks for stopping by. We're pretty close to getting the signal flowing through everything. So I have to reshape this into a fat vector. Okay, flat and everything else. So batch and everything else. Then I reshape it to this product, and then I pull out these dimensions, and then we're done for good. Except I got some shapes wrong. Oh no, it's in the out layer probably, right? Yes. Okay, so I got the reshape wrong, which is good because that's exactly what we're working on. Why did I get the reshape wrong though? What did I do here? Let me see what I did here. So X shape 326144. Oh, because my outlayer doesn't have hidden dim size. It has hidden dim times. No, not for this one. This is the whole point. I did the whole thing from scratch. It's just for fun though, yeah, because this is supposed to be very basic stuff, hopefully useful for somebody. So I know what's happening here. So the hidden dim is 1024, so it has to be times. So this guy needs to know sequence input. Okay, so the transformer needs one more info. It needs input sequence length, because it needs to know what to reshape from. Okay, so this will be input. There we go. This is the final piece now. Input sequence length times the hidden dim to the, and actually let's call it nicer then. Okay, so this is output sequence length. Okay. And code book length, sure. I guess we can call this in sec length. Okay, sorry, I'm fiddling with these. And then out sec length. Right, so the last layer just goes from hidden dim. So, okay, so yeah. So this crunches everything, and then logit is actually output sequence length. Okay, and I need to pass this to the transformer. I also changed the order of arguments, which is not the best thing to do. Where do I get the transformer? I guess this is good that I annotated them like this. So number attention blocks. What did I call this? Out sequence length. Okay. And what is my input sequence length? It's 2 times the number of digits, because I'm summing. I wanted to take 2 numbers, right? Okay, once again now. Okay, very good. We made it to the loss. Still not quite there yet because I'm dumb, but let's see it. We'll just breakpoint here. It's all about shapes. I don't know, whoever that first person was, the first viewer, if you're still here, you are right. It's all about shapes. And I obviously have trouble myself too. So now I come out with logits exactly as I want them. Yeah, these are blowing up, so oh my god. So we're gonna have numerical degeneracy, but sure. So funny. And labels.shape. Oh, the labels are wrong. They're supposed to be 32, 4, 10. Actually, it's just sum of labels then. Yeah. Okay, so this is simpler, but... So who gives me... Why are my labels so warped then? One hot result is wrong? The function that I bragged about? I guess it is wrong. Interesting. Let's see what's happening here. So, yeah, this is way too big. So what's happening here? Codebook dim is what? 10, of course. And numbers is 32, 4. Okay, so what's the problem then? Reference is what? Aha. Tile -1. Damn it. There we go. A teeny tiny change. Yep. And what is one hot encoded? And is it actually one hot encoded? Yes, it is. Okay. Yes, another one. This should be it though, because we made it past the loss. I guess we'll see if the gradient flows. If it doesn't, we'll have to fix it. But that's just PyTorch. That's not me. Breakpoint again. Oh, interesting. Okay. Almost there. The stupid, what is it? Digits to values. Oh. Oh, I see. Sorry. Device. Digits dot device. Okay, so always respect the device. Okay, transformer's working. So, okay, it did numerically degenerated though. I see, so it's predicting 0 for the sum. Oh no, because it's nan, right? So that's gone. Okay, so we have some numerical issues now, which is not the worst thing ever. Maybe we need some normalization. So why do we have some numerical issues? Let's see. Let me look at the output logits. Actually, this is way too fast though. If step 100 is 0, because it's training super fast. We're very close to actually getting this working. My question is, why does it numerically degenerate though? Interesting. Let me do this here. So if step index is 0, let's see what's happening here. Okay. Okay, so the loss is gigantic. So the logits are gigantic. Okay. Oh yeah, because I'm inflating energy, right? So I just gotta tame my data a bit. Let me conserve data energy then. So what I do is I go in through a linear layer. Okay, so we can do a bunch of stuff now. So random, these weights are probably exploding, right? So let's make these smaller. How do I make... Oh, yes, because I have to instantiate like 1 over... Oh, yeah. These layers are... Okay, this is easy to fix. The layers have gigantic weights and they blow up the energy. Good. So how do I sample a tensor with a... let me see if I remember this. Torch random divided by 4. Oh, no. So if I have a random 3, 3... Actually, I don't need the size here at all. This is cleaner. So is there no standard deviation to this? No, I just have to divide it by 3, I guess. Right, so we can do weight in it. We can just take them here and divide it by torch square root. I'm gonna do in dim times out dim, because I vaguely remember that it's something to do with energy, right? And that's it. Self weights. I do a parameter with the weight in it. Yeah, surely I messed up the layers. whoops, torch square root out dim. Now there is some trickery here with PyTorch because I really hope it's going to register these properly. I don't think you're supposed to divide with numbers. Looks a bit sketchy, to be honest. Let's see what's happening. Oh yeah, I can't even do, god damn it. Okay, I'm just gonna, this is so annoying because I can't, I have to do torch square root of torch tensor of this. And I have to give it a D type too. But this is a one-time thing though, because see, and I'll bet you that torch square root of a single integer works. It's just the product that doesn't work because PyTorch has some weird rules. I was wrong. Never mind. Yeah, and I have to cast this to float 32. Okay. Okay, the loss looks a lot more human now. That's it, so I can let it go now. Well, let's see if it works. Is it training or is it not training? 10,000 steps. The loss still degenerates numerically, and it's I don't think I have to minimize logits. Sorry, I have to sorry. The cross-entropy loss is something else, right? This is what I'm messing up, which should be pretty easy at this point. Do I remember the cross-entropy? I don't think I remember the cross-entropy loss, because, yeah, I don't want to minimize logits. I want to do... Oh, I need to do softmax. I need to do stable softmax. And... I take the log of the predicted probability after stable softmax. Okay, so it's not quite like this. So I'll do like this. So stable logits, it's exactly the same as before. Minus, I guess max, we have to stabilize the logits first, right? So max logits is torch.max logits dim minus 1. Stable logits becomes this minus max logits. How did I do it? Torch.max. How did I do it before? Here we go. Let me peek at this a bit. Okay, so max logits broadcasted to the last axis. Then the probs become exactly this. So the softmax of the logits divided by the... So it's just the softmax of the logits, okay? And the loss, the log probs is just torch.log of probs, okay? So now the loss is, we want to minimize the negative log probs, okay? So negative log probs, now this is, I know it's really, actually let me just do it nicer then. So it's the sum, this is the cross entropy, right? Because it's sum of minus log times probability. Okay, another pass. Let's see if this one does, this should be stable, more stable now. Okay, is it train? No, it degenerated. Why did it degenerate? Actually, it was kind of close to learning-ish. What is degenerating then? It's the log, right? Ah, yes, because I take the logs of all probabilities and I get like a minus infinity or something, I'll bet you. I will bet you that's what's happening. So let's see, if log probs is nan.any. Now we're back in numerical world, or more engineering world, because we have to debug. There we go. So we got the nan already. Oh, interesting. Oh yeah, everything is nan. Because why? The probs are nan? Yes. Oh, interesting. Because the logits are nan? Yes. Okay. So what happened here then? Okay, so we have to stop here. So yes, I did get output logits nan. Yeah. What was my previous loss? So I did have some nans in my previous loss. And then it all went downhill there. So the root cause of it is the loss, because I'll bet you the model dot parameters, whatever, is nan now. Oh, actually, wait. I have model dot, what is it called? Attention blocks? No, in layer, for example, right? Or layer dot weights. Yeah, they're all nan, and they have a grad, which became nan from the previous step. So somewhere there's a numerical degeneracy. Oh, thanks for a Twitch follow. Sorry, I'm just seeing it right now. Sorry about that. If you're still here, thanks a lot. Appreciate the follow. Now, what the heck are we doing here though? Because where is the interesting. Where's the degeneracy? Minus stable log probs times labels should I do it this way? Let me see. So what is the log probs shape? And what is labels shape? If I just index log probs at labels. No, this doesn't work. Labels is not. Oh, I see. To torch.long. And what does this give me? Something horrendous. Yeah, it does broadcasting. Well, this is so annoying now. So I know I need to minimize. I have to look at the torch cross-entropy loss because I'm doing something wrong. Am I? can I figure this out by myself? So, what the heck is log? Is it log natural? Yes, it is log natural. Props should be stable though. No, because some of them are 0. That's what's happening. So some of these are 0. Okay. And infinity times 0 is undefined. Okay. So check this out. So if I do if you run Python, I know what's happening. It's infinity times 0. Import torch. Torch.inf times 0. Yep, there we go. So some of the probabilities get so tiny when they get multiplied with 0. Okay, so we do the epsilon trick. Plus 1e minus 7. The cheapest trick in the book. All right. Or let's not do the epsilon trick. Let's just maximize the probabilities. Okay, so I need to figure out how to index probs with labels. Okay, so who calls this one hot result? Let me see how this is called. So there we go. So one hot result comes from batch result, which is actually the labels. So we could directly use batch result. So now I have batch underscore result. Then I have output logits.shape. Can I just index it on the last axis though? Let's see if I can. If I just do this, it's not gonna work, is it? It does, but it gives me yet. Again, I don't remember. Fancy PyTorch indexing. Come on. So I have a batch of indices. I have a matrix of indices, and I want to index the third axis with them. I know how to do this, I swear. Torch A range, 132. For each. No. This indexing is tricky. Yeah, so we don't want to multiply minus infinity with 0, because if some logit goes very low, then the probability will be almost 0. And the log probability would be minus infinity, unfortunately. So the log stability trick is here then. Okay, let's do the... Okay, this makes more sense. Sorry, I was actually doing the trick wrong. Yeah, let's stabilize the logarithm. Actually, stable log is a pretty well-known trick. Yeah, it should be fine. It's just stable log. There we go. It's... is it degenerating? It's not degenerating, but the loss is not going... Well... It's doing stuff. Is it learning the addition of 2 3-digit numbers? Not quite. Well, this is it then. So we definitely know the model changes. Okay, so now we're finally in the, I guess, hyperparameter tuning space. Can we make this transformer learn 3? Actually, this may be a bit harder because I remember some. Okay, the reason why maybe this is a real interview question. This may not be as easy. I mean, we coded everything up. Okay, good. Now, how the heck do we make it work? So we train on 10. How many pairs of 3-digit numbers are there? There are 1,000 times 1,000. Exactly. 1 million. Okay. So let me train on more data. Okay, so let me train on 100,000 samples with a much larger batch size of 512. Let's see what happens now. This is the most basic thing, right? Like just jam more data, larger batches, because I may have just been overfitting that. Maybe. Okay, the torch I need to mean, not sum. Okay, so another anomaly I see here is that I need to do, sorry, the loss, not the torch. We need to do loss dot mean of backward because we want the loss to be invariant to the batch size. So we're going to stabilize learning gradients a bit. Now it is still oscillating. Okay, we're definitely getting stuff. Let me see how it does on the GPU now. Okay, so this is taking up 2 gigabytes, but it's actually very efficient because it's sucking up all my power and my room is going to heat up. But the learning has kind of stalled. No progress. Okay, good. Maybe my learning rate is too... Okay, so of course, because I didn't do anything to add W. Where's my optimizer? Okay. So, learning rate, it's probably too high. We use the legendary 3 times 10 to the minus 4, which everybody uses and maybe it magically works. It has weight decay, which is good. Let's use this. Let's leave weight decay in. Okay, so from here on, it's all ML tricks, right? Like architectural improvements or what we would call hyperparameter improvements. Let's see. Okay, lower learning training loss is going down. Good. Okay, so it's not unstable. It's not jumping anymore. It didn't jump to 50 or something, so it's staying in that space. Now, whether it's managing to learn, maybe, maybe not. Slowly. Probably not. It's still kind of... it jumped. Okay. So there is a spike, an oscillation. Okay, more stuff. Very good. What else can we do here? Number of attention blocks. Let's make it drastically larger. Let's double it. Let's increase the feature dimension. Doesn't matter because you enter with the code book, right? Also, I forgot to do, there's no positional encoding, by the way. Which is probably kind of fine. Maybe that's not that important. Okay, so we doubled the model size. It's definitely slower. And it's definitely not progressing. I mean, some of these answers don't look too far off, but that's not how it works, obviously, because they're all in codebook space. Yeah. So the training has stalled completely now with a deeper model. Okay, so I need like skip connections or something. Yeah, this was not a good idea. Let's try a shrunken model. Maybe a shrunken one will converge to something else. Still hovers around that 7 value. Well, from here on, it's there's no theory, unfortunately, and not much that coding can do. We probably want to do systematic sweeps. Okay, so this one is not the worst. It's jumping up, down. It's kind of it's not the worst. Again, what's printed there doesn't matter because it's The digits have no meaning, right? It's either you get most of them right or most of them wrong. Oh, actually, loss is going down here. Oh, okay, okay, okay. It's actually going down. Okay. Oh my god, it's actually going down. Okay, so a smaller model is something for sure. It's very oscillating, but it is going down. We saw 6.4, which is not the worst. But yeah, who knows what the optimal loss is, right? Interesting. So it would be log 1. Okay, it lost the plot. Okay, well, I don't know how to... I think this is it. So let me just check one more thing, okay? Because I want to see that the model actually changes and all the backprop works and everything, okay? There's probably a bunch... I probably got attention wrong, to be honest. But this is all I got at this time. So what we'll do is... Okay, so here's what we'll do. So let me check the model first. So it has model dot attention blocks. 0, the first block. Q layer dot weights. Okay. So let's remember these. And let's hit continue. See, this is what... Oh, no, they do change. So my learning rate is way too small. I can see some vague changes here, but very small. So maybe if I make the learning rate like... maybe 6 times 10 to the minus 4. But in any case, I just wanted to validate that... Sorry, the model, well, we can check the outlier weights, actually bias, right? Yeah, it changes. So training works. Okay, that was my point. Like, it's not a dead... This is what you always want to validate, by the way. If you're a beginner, well, even I'm not the beginner and I have to validate it. But it's good to check that your model weights actually change, because you may have slipped something and no training actually happens. So yeah, I increased the learning rates. Probably not going to do much. From here on, it's only architectural improvements and whatnot. So this was it. We ended up coding a transformer which did not successful. Well, it doesn't train because I probably missed a bunch of stuff. Let's see what I missed then. Okay. So now we can finally allow ourselves to look. Let's see. So if I look at attention is all you need. And if I knew summing numbers with a transformer, probably missed a ton of improvements, right? So tiny transformers can add 2 10-digit numbers to 100. This is what I want to, this is kind of what I wanted to do, right? Build the smallest transformer that can add 2-digit numbers. So, okay, so there's a bunch of tricks. Like, I don't know what the heck is happening here. Ropes. Yeah, quadratic tied embeddings. We don't have any of these. We just did the most basic thing that does not work. Let's take a look at one of these. This is kind of what I wanted to do. Yep, vocabulary size, output digits. There we go. Exactly what we did, right? Looks awfully familiar. But the thing is, they have a bunch of... There's a rope. So I missed positional encodings. There we go. So cosine sine. So there's a trick called positional encoding where you add this rope to your input. There's a causal mask. I didn't make my transformer causal, but it doesn't matter. There's RMS normalization. Yeah, root mean square. Factorized digit embedding. Oh yeah, I didn't do multi-head attention. I forgot about that. Sparse one-head attention. There's a bunch of normalization tricks here. A lot, like, what the heck is this, dude? There's like minus 22. I guess why not minus 23, right? Wild. Otherwise, I don't think I got the attention wrong. Yeah, there we go. So torch matmul, attention V, right? So scores, there we go. Matmul, there's a scale for the scores. Oh my God, there's a 2-hinge ML. Yeah, okay, so there's a bunch of tricks. This is kind of where I wanted to go, and obviously it doesn't work. Now, these only have 6 parameters, so we weren't able to get it with... Oh no, the trained weights, it only works with 36 parameters. Okay, so it's actually hard to learn from data then. It's harder than I was expecting, but yeah, like the activations are super complex. Oh, even with 6,000 parameters, you can make it on this leaderboard. So it's not that easy of a problem. But of course, Claude Code can optimize stuff like this. Let's see, did I get anything wrong in the attention? Probably I missed a bunch of stuff, like a crap ton of stuff, right? I missed the add and norm. Okay, and I missed the multi-head. So I missed the normalization, actually. Because, I knew there was a residual here, okay? I remember there was a skip from values to output, but there's normalization too. And I also missed the multi-head attention, which unfortunately... And there's probably, yes, there's also... this I didn't. Oh, there's a scale. I missed the scale here too. I wonder what did they use for... Oh, I missed the scale. Square root of D. This one we can fix, just the last one. Okay, so we can just do square root then. My bad. Why does he do... Oh, he dampens, because they dampened the softmax. There we go. Okay. Now remember, we didn't use PyTorch's softmax, so we wrote it ourselves. That could also be wrong. See, there's a scale here. Square root of hidden dim. Okay, so let's do this one. This is the only thing I'll do. Divided by torch square root of self hidden dim. Because I think this is a very important stabilizer. It's probably not going to do anything, but just for fun. So we have the right, we're getting close to paper. Had we seen the paper, we could have reproduced it. And I really, really, really hate this. I guess I have to tensorize this, sure. I'm just going to do something horrible, but I really, really hate how PyTorch does these things. Oh my God, well, what do you know? Oh my God, it's actually training. Well, that was it. See, I missed, you missed, there we go. So it's, well, we don't know. It's definitely helping, right? Like a tiny, teeny thing like that scaling helps a bit. Now, whether it'll crack the problem or not, probably not. But it is, oh my God, it may actually will. Maybe it actually will. And you can actually see the numbers getting closer, which is wild. There we go. So you miss a detail. Got to be very careful with these things. Yep, it's all working. So we're actually learning addition. You can see the results get closer in most cases. Oh, there's a right one. 50 plus 342 equals 392. Done. So yeah, watch out for details. And that's it. So how long do we take? Not too long. Very nice lesson at the end here. Really happy we did it. Yeah, thanks for watching. Thanks for sticking around. I'll put a YouTube video with this and I'll publish a gist on this code if somebody wants to mess with it. But it's pretty successful for 2 hours, 3 hours. So thanks for stopping by. See you next time.